I want to talk about planes in space, but to start, I want to talk about lines in the plane. In the very first video I posted in this section, we actually found the equation of a line in the plane that passes through the point 2, 2, and 5, 6. And we found that equation to be this one. What I want to do now is I want to write this line down in what we call the general form of a line, where I get everything on one side. And so there's that equation of my line in its general form, right? I have a nice slope intercept, but if I get everything on one side, I'm looking at this. Actually, I'm looking at this, but I decided to multiply by 3. Because when I look at this, well, this looks familiar, right? I see a 4 and a 3, and here I see a 4 and a 3, but they're kind of swapped. The thing in front of the x is the j component of this vector, and the thing in front of the y is the opposite of the I component. And so I want to think about that little vector. Where I swap the components of this vector that was parallel to my line and make one of them the opposite of what it used to be. Pause the video here and see if you can figure out what the relationship between these two vectors is. Okay, well, if I think about these two vectors, I swapped the x and the y and made one of them negative. If I'm thinking in the language of slope, I flipped the top and the bottom and made one of them negative. These have to be these have to be perpendicular vectors. In the language of vectors, if I do a dot product, I get 0. And so I just create a vector that would be perpendicular to v, also perpendicular to my line. And I could say perpendicular, I could say orthogonal, I could say normal. When I'm looking at the general form of the equation of a line, I can actually always write it down like this, right? Where these two constants are actually from a vector perpendicular to L. What's even better than that, I could have actually thought about this as the point 2, 2, 0, and the point 5, 6, 0, as if I had a z-axis coming out of the board and up towards the camera. And then this wouldn't be the equation of a line, right? Because z gets to be anything at once. I would get a whole plane, like a wall, coming straight perpendicular out of the board towards the camera. So there's a way to talk about planes in space like this, but what we'll be required to know is a vector perpendicular to the plane, rather than a vector parallel to a line. And we can actually think about that vector as helping me understand the tilt of the plane. Right? If I imagine this to be my plane on an angle like this, a vector perpendicular to the plane tells me exactly how it's pointed. Let M be a plane passing through the point P naught, which x naught, y naught, z naught, and is normal to a vector n, which is a times I plus b times the vector j plus c times the vector k. Now, the last time I used a little n to represent a vector was way back when we were talking about cross products, and in that context, little n was a unit vector. I am not guaranteed that here. N is just some vector that's perpendicular to my plane. It might be a very long vector, it might be a very short vector. I don't know. I do not know the magnitude of n. So I'm going to try to draw a picture here. I'm going to imagine this rectangle I'm drawing to be a plane. So we need to imagine that it extends as far as it wants to in any direction. And I have this point P naught. I want to imagine a point P that's any other point in that plane. And so I'll just let it be x, y, z. And the only other thing I have is a vector that is normal to that plane. So some vector little n that's orthogonal to that plane. Well, I'm going to construct a vector between P naught and P. The vector P naught P would then be x minus x naught, y minus y naught, z minus z naught. All right, well now I could imagine sliding n around so it starts out of P naught, and since the vector P naught P lives in my plane, it's perpendicular to that vector n. Another way to think about that is every vector in this plane has to be perpendicular to n, which tells me that n dot P naught P has to be 0. And right there, I actually have an equation that would describe a plane, and we call this one the vector equation. The vector equation of that plane. Very kind of boring, but it's true. What I want to do now is actually think about the dot product between this vector and that one and actually get a rectangular equation. All right, so vector n, well that was A, B, C. We just wrote down that P naught P was x minus x naught, y minus y naught, z minus z naught, still equal to 0, and I can actually write out this dot product. And right here, we can pause and realize that this actually justifies what I claimed about this being the components of a vector normal to my line, because if I just let all the z's be 0, I get that same equation, so in the plane that has to be true as well. This is called the component equation. Of a plane. I can simplify this to get what we're going to call the simplified component equation by distributing the a, b, and c through, and then moving the ax naught, by naught, cy naught to the other side. And so on the left-hand side, I'd be left with ax plus by plus cz is equal to, well, this would be a minus ax naught, so when I add it to the other side, it would be positive. And this is the simplified component equation of a plane. And I'm going to write that one more way. The equation of the plane passing through P naught, which has ordinates x naught, y naught, and z naught, and perpendicular, or normal to n equals a, b, c, is ax plus by plus cz equals d, where d is the dot product of n and a vector that points at P naught, that position vector pointing at that point. Ax naught plus by naught plus z naught.